She's an expert on the subject from all different points of view, so you can ask her any questions you like. And you can go ahead.
Okay, thanks. Thanks a lot to the organizers for having me lecture at TASI. It's I attended TASI 11 years ago now, in 2009, and it was a wonderful experience. I learned a lot, and it was amazing to be in Boulder. I'm sorry you all can't be in Boulder, but I hope you all interact a lot, because that was a big part of it for me, was some of the, like, people I, to this day, consider some of my closest colleagues or people that I met at that time. And so it looks like from the Slack channel, you guys are taking advantage of the opportunity to interact, but I hope you do that as well. I don't have a TASI shirt because I threw it out a few years ago thinking that, yeah, when I was at well, I don't know if I should say that. The TASI shirt I had was too small because there was a big debate as to whether they would order women's shirts or children's shirts for the women because there were so few of us. And we ended up with children's shirts and it fit crappy. So I threw it out, but otherwise I have a TASI shirt that I'd saved for some time for this moment. But anyways, okay. Please ask me questions. I appreciate that very much, and I hope you ask me good questions that, you know, I have to look up later, because that's fun for everyone. The goal here is introduction to cosmology. And let me start by telling you what my goal for these lectures is and the plan for the lectures, and then I will start lecturing. So my goal is to introduce cosmology at a really kind of big picture lecture with the framework that we use to do calculations, the observables that exist, the interpretation, and give you all sufficient conceptual understanding that, you know, I know some of you work in cosmology. I was browsing introductions, but for those of you who don't, who are mostly phenomenologists, to give you all like a conceptual understanding where you know what types of constraints may be able to come from cosmology, or what the assumptions are and how we measure things and interpret them, so that you know that stuff exists and then can try to learn about it later when it matters for your own research. And then enough of the technical details that hopefully it's a little bit of a foundation that you can use in your own research. So so with sufficient detail for you to apply this to constrain new physics, etc. Or better yet, come up with new ideas for testing neutrinos and other dark matters that we don't yet know about. So for instance, to know really well what the 6 parameters of the 6 parameter model are and where they come from, why we know them, and what it takes to add more. Stop me if you can't read my handwriting also. Okay, so the plan for lectures is as follows. Today, lecture 1 will be a really big picture overview of cosmology, and starting on thinking about the smooth, homogeneous, and average universe. Thermal history, important transitions, test of the cosmic history. And then lecture 2, we will finish. Okay, so this includes thermal history. Smooth universe plus thermal history. And somewhere between lecture 2 and lecture 3, we'll start on the inhomogeneous universe. So this will be what's called cosmological perturbation theory, and we'll discuss initial conditions and evolution and the cool things that we learn about the universe from studying the inhomogeneities of the universe, which is where most of our information about cosmology comes from. And lecture 4 will be more on the inhomogeneous universe. So this is perturbation theory, structure, evolution, initial conditions, etc. Will be inhomogeneous universe continued, plus other things that fit in due to time. So this will largely be data like CMB, galaxy surveys, maybe something about 21 centimeter, future data, and maybe some current puzzles. Okay, so that's the plan. So now I will start. Oh, okay, there's a little bit of a delay. I'll just go to a new page entirely. Okay, so lecture 1, overview. I should keep track of time more carefully. Okay. So here I'm going to start talking about the assumptions and framework for doing cosmology, and then observables and interpretation. Okay, so if I wanted to be super general, what I would say that the assumptions that we make in order to do cosmology today, modern cosmology, physical cosmology, where we use data and calculations to make claims about the history of the universe and the types of matter. I think the assumptions that we make are the following. We make an assumption about that general relativity describes gravity in our universe, and sort of at an absolute minimum, this has to be since the epoch of Big Bang nucleosynthesis, which is when the temperature of the universe is about an MeV. So that's really low energy scales compared to scales of new physics and even other things that we study. But in terms of data points, that's really the first epoch in the universe that we have the most concrete data about in terms of comparing things that people can measure in the lab to what the relative abundances of different types of atoms. If you want to talk about dark matter production, then you need to have assumed general relativity describes our universe up to the mass scale of dark matter when that was thermally produced in the early universe. And if you want to talk about inflation, then that's even, you assume general relativity holds, up to the inflation scale, which can be pretty, only, not so many orders of magnitude below the Planck scale. So depending on when you want to start, you need general relativity. We assume a cosmological principle. And by this, I'm going to generalize it that, oh, actually, I separated it into two things. So our spatial location is representative of the universe as a whole. If we picked a random location in some other galaxy, we would get basically the same measurements. We assume, and can follow up on with studies in more detail, but I'm going to keep it as an assumption here, which is there's some sort of separation of scales, or I'll call this the averaging okay assumption, meaning that when the universe is actually incredibly inhomogeneous, we're like on Earth, in the galaxy, our galaxy has supermassive black holes. Most galaxies have all kinds of black holes. So the actual spatial inhomogeneities in our universe are gigantic. Yet we work under the assumption, which can be proved to a certain extent, using various methods, that we can still, even as you go to large scales, the universe appears very smooth and homogeneous, and we can still describe the large scale properties of our universe by averaging over these small scale things. So I don't need to understand what's happening in a black hole to describe the universe as a whole. So there's some sort of separation of scales that we can verify. We'll do some linear perturbation theory calculations and then go beyond that, but I will never go beyond it in cases where I have to worry about general relativity. So here's where you can add new physics if you want. A cosmological principle for the laws of physics, meaning they don't vary in space or time. Okay, and all of these are tested by data. So even though I make them as assumptions, that's a fun thing to think about. So, okay, so this is assumptions, and then the framework. Oh, I think I see a question. Okay, good. Okay, the question is, are there clear indicators to know when these assumptions are failing? So, okay, so I guess there's two ways of saying this. So one thing we do is we just test. So for instance, for general relativity, there are many tests of general relativity on different scales, and that's something people go out and look for and write papers about, and they construct indicators which I'll mention some of, like consistency. There are consistency checks that the universe being described by general relativity has to satisfy. The cosmological principle, the universe is, we really don't know if our location is representative, but we can see out to incredibly large volumes in the universe, and it definitely appears to be the case that other regions look the same as we look. Although we're the only place in the universe that we see at this instant in time. Everything else we see in the past, since it takes light and time to travel. There have been some arguments as to whether this kind of averaging stuff, if you do the averaging incorrectly, then maybe there's some sort of back reaction of nonlinear stuff on small scales, which corrects the expansion of the universe on large scales. And I think the consensus in the community now that's been discussed from a variety of methods is that that doesn't work. But that would be an example. And then of course people do things like, for instance, look at the fine structure constant in different, look at atomic transitions in different directions to measure the fine structure. So this is, some people make their careers testing these things. And that's part of what we do. Now, it could be that there's some tests that nobody has constructed that, it could be that there's something confusing in the data and nobody's had the right test to identify what that is. But I don't think there's anything that's at that level. Does that answer the question? Okay. Okay, move that chat. Okay, framework. So, okay, so cosmology is a series of applications of Einstein gravity, meaning, Einstein's equation plus the continuity equation and the geodesic equation. Oh, I see it. Another question. Okay, I think that's fair. So usually when people say, okay, so the question is, what besides the laws of physics are we assuming our location is representative of, i.e. how is point 2 different from point 4? So usually when people say the cosmological principle, they're not referring to the laws of physics, they're referring to like the amount of stuff. So like the types of matter we see locally, the fact that from our location, the universe appears to be expanding isotropically in all directions. So this first point is usually about like the distribution, the types of matter and how they're distributed. So like the solutions, let's say, to whatever your theory is, whereas point 4, I'm saying, you know, we understand E&M now, we can use E&M to calculate scattering processes far away from us, and that's reasonable. Okay, thank you. Okay, Einstein gravity and geodesic equation. So a tangent vector, some parallel transport, plus Boltzmann equation. And I'm going to schematically write the Boltzmann equation as follows, which will be dFi equals C of Fi, Fj, ... Where this is the phase space, this F is the phase space distribution for species I. And this is a collision term if there are interactions between different species. And it can depend on species I and, you know, J, K, etc., other species. So that if something's not interacting at all, then it's just that phase space density is conserved and a generalized in general relativity. If there are collisions, like photons scattering off of electrons or whatever, then they're captured by this term here. So so e.g., you know, F is like F gamma, the photons, or F electron, positron, blah blah blah. So cosmology is a series of applying these equations. These are really hard equations to solve in general. So usually we solve these perturbatively. And what this means is that we assume that the metric is a metric which has the symmetries of a Friedmann-Robertson-Walker metric plus some perturbations. And for now, I'm going to stick with linear perturbations. So so this is a metric with spatial homogeneity, anisotropy, this is a metric with spatial homogeneity and isotropy, and in a universe with spatial homogeneity and isotropy, it's possible to choose coordinates such that the metric takes this form. One example of coordinates that take this form are ones with line elements. I need to write this down. ds squared equals minus dt squared plus a squared of t times dr squared 1 minus kappa r squared plus r squared d omega squared. Okay, so this is the Friedmann-Robertson-Walker metric in 4 space-time dimensions with coordinates with spherical symmetry. And this a of t is a function of time. So not a function of space. And so let me just write it like this instead. Kappa is the spatial curvature. It's called the spatial curvature, and it is constant, some constant. Is there another question that I missed? Oh, sorry. Would there also be diffusion terms along with collision terms? I'm actually not sure I understand the question. So the okay, so I'm not sure I understand. So the question is, coming back to the Boltzmann equation, would there also be diffusion terms along with collision terms? So this is saying I have a bunch of particles and I'm tracking them. I have many particles, and they all have individual momenta, individual positions.
Hi, can you hear me? I was the one who asked the question.
Yeah.
So I was just wondering if I mean, there are these scattering things, but you would also include, like, let's say a gas of particles, they would just sort of diffuse out on their own. Would you include something like that?
Yeah, I guess I don't understand what you mean by something that's not captured by just the phase-space distribution.
So like there's no dependence on position. Is that what?
Oh, this is schematic. This is totally a schematic equation right here. These F's are in general functions of position, momentum, and time.
Right. So you would have like a spatial distribution of these species and things like that. That's what I meant by diffusion when I asked the question.
Yeah. Oh no. Yeah. So let me just add these. So this. So F is a function. Will be a function of space. You have to pick a slicing in your coordinate system to define it correctly, but it can be a function of X, F, P, and T. And this equation here is totally schematic. So if there's no collision terms here, then we'll write this down momentarily. But this is dF equals 0, meaning that there's no the number of particles is conserved. But if I'm in an expanding background, then this isn't just constant. It's not just trivial. It'll have some time dependence.
Okay, thank you.
Okay, sorry about that. And definitely, if somebody can interrupt me if I don't see the question at the right time. Okay, so this is an example of the FRW metric, and we'll elaborate on this in a little bit. But right now, I just want to give an overview of what it means to do cosmology. Okay, so typically we solve this perturbatively, and we usually work in situations where we can either solve this linearly, or in cases, fortunately in cosmology, in most cases where you need nonlinear corrections, you're actually in the Newtonian regime. So that works. The delta GAB are perturbations to the metric, and there's important things. There's no restriction on the symmetry. There's no, what do I mean to say? I mean to say there's no symmetry restriction on the form of delta GAB. So the FRW metric example here, the existence of spatial homogeneity and isotropy severely restricts the form of the metric. It allows you to go to a coordinate system where the metric is severely restricted. Question? Oh, for now it's just a function of time. We'll go into the physics of what it is, but the symmetry of Friedman, Robertson, Walker. Should I do an aside on GR for a few minutes, or should I?
Up to you.
Okay.
If you want to poll the students, we can get a show of hands.
Okay. 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 Let me. All right. Let me. Okay. if there's one person who says yes, then I'm going to do it. And it's going to take 2 minutes and it won't be in so much detail. For almost everything, you'll just get to use equations that I'll present straightforwardly. Okay, let me finish writing this. Actually, what I will do, how do I do this? Let's see, I can, let me, I want to cut and move this. Okay, hold on. I think I can cut all this stuff and then put it somewhere later. Oh, I think that's not going to work. Okay, I'll just start here. Okay. Okay, so this is a lightning intro to GR. Okay, so general relativity, very briefly for our purposes here, is a theory with the dynamical variable is the metric, metric GAB. So this is GAB, and GAB tells you how to calculate distances beyond Minkowski space, beyond flat static space-time, like Minkowski. GAB, one way of thinking about it is considering it to be a symmetric 4x4 matrix of functions of space-time coordinates. And so that means that there are basically 10, this is some thing that we use as our ruler in dynamical space-time with mass, and it's essentially 10 free functions. So, and then, Minkowski would be GAB equals the usual Minkowski metric, eta AB, which is just those diagonal pieces. So a generic solution, and so, okay, so the dynamical variable is this metric, GAB, and it has to be symmetric. And if we live in 4 space-time dimensions, then we could write it as a symmetric 4x4 matrix. And every component of that matrix depends on space-time. So that gives us 10 free functions. Now this is the dynamical variable, and we find solutions to this dynamical variable by solving the equation of motion, which is Einstein's equation. And we write this as GAB equals 8 by G TAB, where GAB is a second order in derivatives function of GAB that I'm not going to specify here because it's complicated, but we will do an example. We'll compute it shortly, and I'll just tell you what it is because we don't have time to, because this isn't GR, this is cosmology. So the left-hand side of this equation is some second order functions of derivatives of the metric, and the right-hand side is the source. The source term is the stress energy tensor, and it depends on energy density and pressure. It can depend on viscosity, anisotropic stress, all the stuff that's present. In our case, this is all the stuff in the universe. So this equation of motion, GAB equals 4 pi, GAB equals 8 pi G TAB. This can be thought of as the generalization to Poisson's equation. By which I mean the equation for the gravitational potential in Newtonian gravity, right? So in Newtonian gravity, if you tell somebody the distribution of matter that's present, it's a little slow here, then you use this equation and you can compute phi, the Newtonian potential, and that tells you what the gravitational force everywhere will be. In GR, you tell me, or you measure what all the stuff that's present in the universe is, and then you solve this differential equation and you compute GAB. And that tells you the metric, which tells you how to measure distances, how to measure time intervals, how to measure momenta and velocities of particles. Along with this, we also have what's called the continuity equation. So GR comes with the continuity equation. Which we write like this. And this is a continuity equation on the stuff that's present in the universe. And this is kind of like a generalization of any other continuity equation you're familiar with, but including, du equals p dv for a closed system. Okay, so this is just a lightning overview of like what this stuff, what you need to know, what the metric means. Everywhere you're used to putting the Minkowski metric, now you put the particular solution to our universe, that metric, GAB. So every time you want to compute scattering or whatever, this is the metric that you need to use to compute the momentum, to measure the magnitude of the form momentum. And it depends on the stuff that's present. And that's the end of the lightning overview. Are there any questions about that? That's obviously not a full, it's not a full GR course, but hopefully that explains. So now that I've said that, let's come back. So this asserting that the metric takes this form means what we mean is that we can write this as a background FRW metric, so a metric that possesses the symmetries of FRW. If you impose on GAB that there is spatial homogeneity and isotropy, then you can prove that there exists some coordinate system where you can write the metric in this form. So it's spatially homogeneous and isotropic, but it's not temporally homogeneous and isotropic. Things can change with time. And that leaves you with a metric which, instead of looking like, Minkowski, where I have minus dt squared, and then, just this piece here, dr squared plus r squared d omega squared, I'm allowed to have some function of time here, which is going to change the units of distance in a time-dependent way. And I'm allowed to have spatial curvature, which means that one way of saying that is that I'm allowed to, I get this kappa here that shows up. So if the spatial curvature is 0, then these coordinates right here are just like three-dimensional flat geometry, x, y, z coordinates written in spherical coordinates. But in general, just presuming spatial homogeneity and isotropy doesn't get you back flat Riemannian space. You're allowed to have some spatial curvature, and then you're allowed to have some time dependence multiplying this whole spatial metric here. So we will see shortly when we start studying the expanding, we'll see the consequences of this A of t. The question is, why do we assume kappa is constant? It's not an assumption. The assumption of spatial homogeneity and isotropy forces it to be constant. If it wasn't constant, this is, so I don't have time to do this, but if you take GR, hopefully it could be derived. But the assumptions of spatial homogeneity and isotropy allow you to prove that there must be some coordinate system where you can write it where you can write the metric like this and you're stuck with a free constant here. Okay. Is there anything else I want to say about that? Okay, so coming back to that, so let me, I'm gonna, just to make this a little bit more continuous, I will cut all of this stuff and move it down. Because I should have offered that GR bit earlier. Cut. And okay, so having said that, having introduced GR very briefly, we assume that the metric can be written like this. As a Friedman-Robertson-Walker metric plus perturbations. And I haven't said what makes them small yet, but these will, for now, we'll just assume that I can split the metric into something that's FRW and then stuff that's left over. And the stuff that's left over there's no symmetry restrictions on delta GAB. So this will have 10 degrees of freedom, the full 10 degrees of freedom. Unlike the FRW metric, where spatial homogeneity and isotropy give us this one constant and then one free function here, and everything else is fixed. Okay, and as mentioned, the other side, the right-hand side of Einstein's equations has a stress energy tensor, which we will write in the following. Sorry, my handwriting is getting messy. TAB plus delta TAB, where this is a spatial average, and the symmetries of this TAB respect the FRW symmetries. Okay, so the smooth average universe has the following equations. We'll have Einstein's equations for the FRW metric, which are the solution to Einstein's equations plugging in the FRW metric on the left-hand side, and the average of all of the stress energy tensor of everything in the universe on the right. And we will have a continuity equation, where this is the covariant derivative with respect to the FRW metric over here, and this is the average stress energy tensor. And these two will give an equation of motion for the function a of t. In terms of sources, TAB. We can also have, we'll also have average Boltzmann equations, things like this. And this lets us compute average thermal properties of stuff in the universe. Number densities, energy densities, etc. The inhomogeneous or structure in the universe will obey the following. It will obey some equation that looks like this. The perturbed Einstein equation, there will be a perturbed continuity equation. Oops. And perturbed Boltzmann equations. So this is, I guess I'll say that this is the first order Einstein. That's what I should call it. Okay, so this is a coupled system of linear differential equations. And much of cosmology amounts to solving these equations in different circumstances. This is only the linear terms, but this is good enough to compute most of the CMB. Uh-oh, what's that symbol? Observations on very large scales. Okay. Now, as I mentioned earlier, and we'll hopefully come back to at some point, nonlinear equations are needed for some observables, but usually not in circumstances where we need full GR. So you can do something kind of simpler than trying to solve those equations to second order. The continuity, that's fine. Yeah, I said, so the question is, the continuity equation also comes from Einstein's equations using the Bianchi identity. Why do we treat them independently? That's fine. I'm considering the GR, the set of equations that we solve, to be Einstein's equation plus the continuity equation. But the symmetries of GR force the continuity equation on us. Okay, so we're almost always looking at things less dense than black holes. So cosmology amounts to executing these calculations. during different epochs in the history of the universe. Under changes to what types of matter can be present. Or how it behaves. So this means TAB, changing TAB or delta TAB. Under changes to collision terms. At the nonlinear level, etc. So one thing I meant to say actually is that you'll notice in this super general overview, GR is, so we assume GR and we can solve for the whole expansion history of the universe just knowing the total stress energy tensor. We don't need to know anything about the interactions among particles, for instance. So we just need to know some average properties like the energy density and the pressure of the stuff that's around. So all of the other laws of physics and all of the other interactions only go into these collision terms, okay? So the collision terms here in this equation help us know the properties of TAB, that like what types of matter are present, and the overall properties if it acts like a fluid or not. But all from the perspective of just looking at the overall expansion of the universe and so on, we really know very little or need very little input about these collision terms, any interactions. Okay, so continuing to say that. So what are the things that we can observe in cosmology? Okay, so we can measure redshift, which I'll add on. So as the universe expands, as this A of t function changes, distances are stretched, and that includes, the distance between peaks in a photon. So a photon that's emitted at some point in the universe will, as it travels through empty space, its wavelength will be stretched along with the expansion of the universe. And astronomers have named this stretch the redshift. So this would be photon emitted with the redshift is called Z, and it's defined through this. So this is redshift. Well, I guess not make it bold, but make it color. And this is related to the scale factor, the change in the scale factor between the time the photon was emitted and when it was observed. We can measure the apparent luminosity of things. So how bright something appears from here. We can measure angular sizes. And we can measure time intervals. But we're stuck here on Earth, so we can't go out and measure distances, physical distances between things. We can measure angular distances from things we can sit here on Earth and see, and then use some other principles to try to get a physical distance, convert an angle to a distance. These set of things help determine distances in expansion history. We can measure the temperature of the cosmic microwave background directly. And and deviations, any deviations from black body, from we can measure nearby or local densities of stuff, like the density of hydrogen atoms, the local density of dark matter, the fraction of helium locally by mass compared to hydrogen, etc. And these, you know, give input on types of matter we should include in TAB. And they can give some cross checks. On the thermal history that we compute. We can measure things like the number density of galaxies. The number density of neutral hydrogen. Sorry, I'm running out of space. Of neutral hydrogen per volume, etc. So this is kind of a set of the average things that we can measure. And then important stuff is the fluctuations, which we can also measure. So examples of this are changes, variations in the CMB temperature. And we measure variations in different angular directions. So this would be TCMB in some direction n hat minus the average one over the average one today, and that's what z = 0 means. We can measure fluctuations. We can't quite measure fluctuations in the total matter density, but we can kind of infer it by using gravitational lensing. And similarly, we can measure fluctuations in the galaxy density, fluctuations in the neutral hydrogen density, etc. We can measure variations in the polarization of the CMB, which is characterized by these E and B modes. And let's see. So, okay. Under the assumptions that we've made of homogeneity and isotropy, which appear to be true, these fluctuations themselves on average are 0. And under the assumption of statistical homogeneity and isotropy, the absolute values of these fluctuations at any point are not meaningful. So we don't think it matters that there is you know, a galaxy in a particular direction or an overdensity of matter in a particular direction. What we think the physically relevant things are the, given that there's an overdensity here, how likely is it that there's an overdensity this far away? Sorry, I'm out of the camera. Okay, this far away, or this far away, or this far away. So what are the statistical properties? How are these different fluctuations correlated? So of the fluctuations on their own, the particular, let me put it this way, the particular realization of fluctuations Okay, so for example, the thing that people compute with the power spectrum, with this cosmic microwave background, is they correlate the fluctuations in the temperature in different directions and take an expectation value, where here this expectation value is an average over our own sky. But since we think that our own place in the universe isn't special, we hope that expect that the average over our own sky with suitably many measurements reflects the true average in the whole universe. And so because of statistical homogeneity and isotropy, this correlation function can only depend on n hat dot n hat prime, the angle between the two. And so it's usually written instead in terms of this angular power spectrum. It's 4 pi. But that's Legendre polynomials. And it's called the power spectrum. This can be determined like this, where these are coefficients. Okay. Okay, so we take power spectra, for instance, or correlation functions. Okay. For instance, fluctuations in the matter density at some converted to some position. And we always define things in terms of these power spectra. So this is again called the power spectrum, and this would be the correlation function. Okay, so these are things people can measure. We also measure higher point correlation functions. And cross correlations between different fields. The evolution of these things helps give information. Oh, sorry, I missed it. Does TAB, okay, so the question is, does TAB account for the energy lost by photons when they get redshifted? Where does that energy go? Would we say that the photons are interacting with something? Okay, so TAB, the change in, as photons are redshifted, the energy density in photons decreases. So, and it decreases in a prescribed way that can be determined from, for example, the continuity equation, or the collision equation just for photons if they're not interacting. So if they're not interacting, their number density and energy density will all decrease as the universe expands. And the fact that TAB satisfies this continuity equation in an expanding space-time means that it's all accounted for consistently. And this is fine. And in an expanding universe, energy is not conserved, right? There's no time trend. Normally time translation symmetry gives you energy conservation, and we don't have time translation symmetry in a universe that has this changing metric. As long as this is A of t is a function of time here, then you don't have a symmetry that gives you energy conservation. But all is not lost. The generalization to that is the generalization to energy conservation becomes this local equation, the continuity equation. So this equation in a static universe would reduce to change in energy is equal to 0. But in a universe that's expanding, it changes. Okay, so let's see how I'm doing for time. Okay, and then the separation between where information comes from when it comes to fluctuations is that the evolution of the fluctuations can give info about the types of matter present, and the expansion history, whereas the statistics, where here I mean what is correlated with what things are correlated. So messy, sorry. Correlated, the initial conditions, etc., tell us about inflation, or whatever alternative you might think about inflation, and the very high energy physics of the early universe. Okay. Oh, I might have a typo. So, okay, so the question is, oh yeah, oh no, sorry, that's correct. So this, good. This is a statement of statistical isotropy that one gets this. So for a given L, isotropy definitely has to give you the delta M and M prime. But overall, to have statistical isotropy on all of these things, you also get a delta that different L are uncorrelated with each other. This is equivalent. You can think of this, so maybe in this form it doesn't look so obvious, but I actually skipped writing something right here, which is, so here I take a correlation function and I expand it in terms of a power spectrum. I can also compute the power spectrum directly from these multipole moments. I could do the same thing here for this correlation function. Let me just move that down a little bit. So let's take this up here and write delta rho over rho of k to be equal to then the power spectrum, if I correlate two different Fourier modes, homogeneity forces this to be proportional to a Dirac delta function. So maybe this is more familiar to you as looking like momentum conservation due to homogeneity. And then isotropy forces this power spectrum to be a function only of the magnitude of 1 of the k. So this is the 3D version of the statement here. Okay. Okay, so I think I have 6 minutes. So now I'm going to start doing, so this is the end of a very general overview of what we do in cosmology and where things come from. And now I'll start talking about the smooth average universe and be a little bit more, do a little bit more calculations. Are there any questions before I move to the next part? Okay. Okay, so as I mentioned, under the assumptions of isotropy and homogeneity, the line element can be written in this form that I mentioned, where I'm choosing the cosmologist's metric signature, which is the preferred signature. Okay, so let me just mention this again. So A of t is a function of time only. And okay, sorry. So what do you mean by observing by the evolution of fluctuations? Are we not just observing a static imprint from the CMB? So good point. So in general, we observe the CMB, and we've been doing it for, we've been measuring fluctuations in the CMB since the early 90s, and those fluctuations have not changed because a time scale of 30 years is small compared to the expansion of the universe. So we're still seeing the same slice of the cosmic microwave background. So we can't see the CMB evolve. And in fact, the same thing is true if we look out at galaxies and we measure galaxies. We measure some distribution of galaxies, and we've been doing that for hundreds of years. Those distributions don't evolve, or at least we don't have sensitive measurements enough to see the evolution of any particular stuff in the universe. But if the universe is statistically homogeneous and isotropic, we can compare how the average distribution of galaxies changes from one redshift to another. The CMB is different because we only see the CMB coming from one particular time. But for everything else that we see, like 21 centimeter fluctuations from neutral hydrogen, or the distribution of galaxies and distribution of matter, we can measure that at many different distances from us. And we don't watch any one evolve, but by comparing them on average at different distances, we can study, we can measure evolution in that way. Does that answer your question? Okay. Okay, so A of t is a function of time alone, and you're free to normalize at any t. In other words, A of t is only fixed up to an overall constant. So the convention is that A of t today is equal to 1. And that's just a convention, but it makes things useful. I guess there should be a lower index for the rows, which you mean in this power spectrum definition? Sure, yeah. So let's call this X, and then we can measure correlations between stuff X and stuff Y, and then this is X, Y. Okay. Okay, again, kappa is a constant, and it has dimensions of 1 over length squared. We're also free to normalize kappa by changing R. By reparameterizing our spatial coordinates, and conventions here are that kappa, so you're free to normalize kappa, and so the conventions are that we normalize it so that it's either 0, which you're not normalizing it, or it's plus or minus 1. Kappa equals 0 corresponds to spatially flat universe. Kappa equals plus 1 is spatially closed or positive curvature. And this means that the universe, that spatial, at any fixed time, the spatial geometry of the universe is that of a sphere. And kappa is equal to minus 1 is, people call it open, because you can't, if you have a homogeneous isotropic negatively curved surface, it's infinite. And so this is negative curvature. And an example of this would be the pseudosphere. So given this metric, or given this form of the line element, physical distances, the physical distance interval, which is also called proper distance, is given by just the spatial part of that, taking the square root of this quantity. Actually, I'd like to use different notation. So this is one, oops, I forgot the dx. Oh no, that's actually fine. Sorry, never mind, that's fine. Let's use this notation here, where we sometimes write this as gamma ij dxi dxj. So we'll use this again. This is the FRW, the spatial part of the FRW metric in spherical coordinates, but I could have any coordinates, and so we could just generally write this part as delta ij dxi dxj, where ij means sums over spatial indices. But I'll keep this for now. Okay. Okay, so this is the distance, this is distance intervals that we would measure. And it's the distance that enters into, for instance, scattering calculations. So anything where you're doing something physical, it's the proper distance is the thing that enters, but it's convenient to use coordinates sometimes that just depend on this piece. Question, would it be possible to have a non-diagonal metric that doesn't violate CP? Yes, it's possible to have a non-diagonal metric. Yeah, that's fine. Okay, another distance that we use is co-moving distance interval. And this is where we remove that time-dependent piece, the A of t, and just look at this part. And this describes distance intervals on like a fixed grid. So the physical distance will be changing, but if I set up some coordinate system in space-time where I draw out coordinates and I say, you, Pen, sit at coordinate 1, 2, and I'm sitting at coordinate 0, 1, those are just the labels, and the distance between those labels and the coordinates is the co-moving distance. And that's convenient because something that's just at rest, because things that are at rest with respect to this FRW background, in particular things that are the special coordinate system that sees the universe as homogeneous and isotropic is at rest with respect to this coordinate system. And then their co-moving distances don't change even as the universe expands. The physical distances change, but the co-moving distances don't change. So that's convenient. So let's see. What else do we have? Oh, I went 5 minutes over already. Let me answer this question. What does the perturbation in the context of inhomogeneous cosmology reflect in regard to physics? Are those all due to quantum fluctuations? Okay, first of all, the universe is inhomogeneous, so that those inhomogeneities could just refer to like our galaxy, the sun, other galaxies. That's the universe that we observe is not perfectly smooth. Like we exist, right? So we are part of those fluctuations. We're part of what makes the universe, not exactly FRW. And then there's a question as to where those fluctuations came from. Why is the universe almost so smooth but not perfectly smooth? And indeed, yeah, the theory of inflation gives a prediction for the theory of inflation is our best explanation for the origin of those fluctuations, but they're not quantum today. That's just the stuff. That's just a description of all of the matter in the universe, which is, and the amount of stuff varies from place to place. So I think I've gone 5 minutes over. Is that correct?
You started a couple minutes late, so
okay.
I think we're just about on time.
Okay, should I stop?
You can have a couple more minutes if you like.
Let me, actually, it's not an unreasonable place to stop. The next chunk of stuff is a little chunk of stuff altogether. Okay, if the metric is symmetric, a real symmetric matrix, it can always be diagonalized. So should we always have a diagonalized metric? So the statement here is that it's not a constant real symmetric matrix. Each of those components is a function of position, and you can't so that when you diagonalize a matrix, you're changing coordinates, right? So you don't have, you're changing coordinates, and since the matrix elements are all functions of position, then you need different coordinate changes at every location to diagonalize it everywhere. So everyone individually, you can, the statement that you can locally change coordinates to make it diagonal, you can make it locally Minkowski, but that transformation is different for everyone everywhere. So there's no global coordinate change that can bring the metric into that form.
All right, great. So I don't see any further questions. We do have kind of a longer day today, so if there are any more questions, maybe we can take them over to the Slack. So let's thank Marilena for the very nice lecture, and then we'll reconvene in 20 minutes for our last lecture of the day.
Okay, see you guys tomorrow.